So we move on to India, to Bangalore, where Shashi Jain is assistant professor in the Department of Management Sciences Studies at the Indian Institute of Science, IISc, in Bangalore. He used to be one of my PhD students, and after his PhD, he went to ING Bank in Amsterdam and worked there for a couple of years. And now for some years already, he is back in India and working on neural networks, on Monte Carlo simulation, on real options, portfolio allocation, point processes. And today he will talk about universal static hedging of contingent claims using neural networks. Shashi, the floor is yours.
Thanks, Kees, for the introduction. I just put on the videos to say hi to everyone. Yeah, I told about this workshop he was going to organize, and we were, I was supposed to be there in Amsterdam for a few months to work along with Kees, and it would have been great to be there and be part of this conference. But it's also quite nice that you see that more than 100 participants around the world are listening to your talk. Especially when you don't meet many people, so it's quite nice right now. So I hope everyone can see the slides that I have shared. Is it visible?
Yes, it's very well visible, Shashi. So
okay.
Please go ahead.
Yeah. So thanks again for inviting me for the talk. I'm going to give a talk on what I call universal static hedging of contingent claims using neural networks. I also give a very brief background on how how we came across this idea. Maybe inspires others who are thinking about using neural networks or machine learning. That there is something to it, which is which can help things which are already going fine. So the outline of the talk is briefly given here. So I talked briefly about the background, the motivation for this work that we have done, which primarily started with using neural networks for pricing contingent claims. But we soon realized that it also leads to a general understanding of how we can we can construct a static hedge for any contingent claim, path dependent or otherwise, given certain assumptions. So that's something that I'm going to touch on, where I briefly sort of talk about dynamic and static hedging. Then the main part of the talk, which is, we look at a specific path-dependent contingent claim, that Bermudan option, which is quite, if you can solve for Bermudan option, then it's usually straightforward to extend it to other options. And describe the method, which we call regress later with neural network. And some results, more detailed findings are reported in a preprint, which I share in the references. So how did this all start was, I saw everyone was working on neural networks and machine learning, AI, and I didn't want to miss the bandwagon, and started exploring the area. And one of the ideas we had was, typically when you do American Monte Carlo, the main step involves a linear regression. Now the challenge with linear regression is that you need to select the set of basis functions for your regression, which sort of depend upon the payoff, right? So that was not very nice, and we thought that maybe neural networks would help us to resolve this issue, so that you have a general code where you don't really need to select your basis function depending upon the option you are trying to sort of price. So it started with a pricing problem. and we used the most basic neural network possible for this particular approach. And what we realized was we sort of uh, it can make a claim that any contingent claim can be hedged, statically hedged using a portfolio of short maturity options. Now, this is quite nice in certain aspects, which I'll also discuss a little bit later. Uh, the fact is that we were not the first one to, understand the importance of static hedging or hedge options using static hedging, but uh, I think we are the first to sort of give a proof or make a claim for high dimensional derivatives, because most of the work so far was typically limited to one dimensional case. But the other, nice thing of this algorithm is that it also addresses the point one here, that we sort of have a general framework where you do not need to make choices depending upon the contingent claim that you are trying to, price or hedge. So the structure of the talk would be, I briefly have explained dynamic and static hedging, and then pricing of Bermudian options, with the focus on regress later approach. So regress later approach is slightly different from the more popular regress now approach, with LSMC being one of the more popular regress now approach. While regress later has, was proposed initially by Grasserman, and there was work that we did with Kees Oosterlee, and we call that stochastic grid bundling method, which is also one of the variants of the regress later method. I explained the neural network framework for pricing and universal static hedging of contingent claims. So the most common way of hedging options has been traditionally, the dynamic hedging, which started with the seminal work of Black-Scholes and Merton, who showed that the market risks of the options can be eliminated under assumptions by setting up a dynamic hedge account. So the hedge account would consist of a money market account and position in underlyings, which constitute the option, or on which the option is written. The quantity of the underlying that you need to hold in this hedge account changes with time, and ideally you should rebalance this this hedge account as soon as possible. Although in practice it's typically done towards end of the day. So this is by far the most commonly used approach of hedging options. The issue with dynamic hedging is when there are sharp movements in the market, especially jumps, your dynamic hedging doesn't work, because you cannot hedge against jumps. You assume normal distribution and so on, and this the jumps can cause issues in your hedge account. And also, when you really need to hedge, when there is a sharp movement, the market faces liquidity, and this is the precise moment where you would like to hedge your option. And it is the same time where the liquidity of the sort of dries up, and that sort of leaves you in a not so nice position. This is a common drawback of dynamic hedging. So, for instance, during the COVID time, the markets would have crashed, and you would have to find the underlying to hedge your option, and the liquidity in that underlying would be drying up, and that's a kind of situation that you really need good risk management, and this dynamic hedging can sort of be problematic. The other approach, which is known as static hedging, is sort of nice, and one of the the simplest example for the static hedging is sort of displayed here. So we want to hedge a claim whose payoff at capital T future time is depicted by the right hand side, right? The figure in the figure. Now, the payoff of this claim can be perfectly replicated by a combination of option, that is a long call and a short put. So this is very well known put call parity. Uh, so the payoff at capital T for the left hand side portfolio and the right hand side portfolio would perfectly match. And because they match at capital T anytime prior to T, assuming the markets are functioning fine and there are no arbitrage, the value of the two portfolios should be the same. So if we buy this combination of options, once we buy this, we are always hedged against the payoff on the right hand side. And this is what is known as static hedging. So you just buy the options at the beginning of the, and you don't need to rebalance it every day. So this is quite nice, especially when there are sharp movements in the market and so on. Now, this is a very simple case where you have a very simple payoff which can be replicated by these two options. But can this be done generally for any payoff, right? And especially if you go to a high dimensional payoff, how do you handle that, right? So this is what we are going to sort of address in this talk. What we show is that you can hedge any payoff in any dimension using a combination of arithmetic basket options. And if you can do it for capital T, you have a static hedge whose value will always replicate the value of the claim that you are trying to hedge. Before I go to the method that I discuss, I also sort of briefly talk about the present approach of static hedging options. This was, there are many who have worked in this area, but the most recent work which I'm aware of is from Carr and Wu, who show that a long European option can be hedged with a continuum of short maturity European call options. Where the maturity time of the short option lies somewhere before capital T, which is the maturity of the long option that you are trying to hedge. Now this is a hedge with continuum of option with varying strikes, and the weight W gives the quantity of this option, short maturity option that you need to hold in order to replicate the long-term option, which is given in the left-hand side. So VTT is replicated by short maturity option VTU with strike SU, and the quantity of that option to be held in your portfolio is WSU, where the weight WSU is determined by this particular relation, which is the second order derivative or the gamma of the option. This of course is for a continuum of option, but you can always discretize it and make it more practical by considering finite set of options to hedge your long-term option, and this is what was done in Carr and Wu 2013. Right, the proof of this is what I just displayed was quite straightforward, and it's based on a relationship which was arrived by Breeden and Litzenberg, which is the risk neutral density of your underlying can be computed as the second order derivative with respect to the strike of the option that you are trying to hedge. Using this relationship, you sort of arrive at the outcome of theorem that I just displayed. So I do not go into detail of this, but this is there if you want to look at it. Yeah. Now I move on to pricing of Bermudian option so that I can sort of explain the universal static hedging. A Bermudian option is an option which gives the holder the right but not the obligation to exercise, buy or sell an underlying at a fixed price at certain pre-specified date. In order to price the option, what you need to do is you want to maximize the expectation of a future payoff by following some optimal exercise policy. And this is what is given by the equation displayed here. The exercise times where, the points at which you can make your early exercise are given by T0, 0 till Tm, where Tm is equal to capital T here, for simplicity. What you obtain if you exercise your option at time Tm is the payoff, and it's given by function H. And BT here is the money market account, riskless money market account. For Monte Carlo based method, this formulation is not very handy because you don't know the optimal early exercise policy. Christopher just had an approach where this optimal early exercise policy is learned. We take a separate, a slightly different approach, which is following a dynamic programming principle. Where we directly try to learn the value function rather than the optimal early exercise policy. So the dynamic programming formulation of Bermudian option pricing is sort of discussed here. What you do is you simulate your scenarios, risk neutral scenarios of the underlying asset up till capital time T. At capital time T, you know the value function, which is VT. It's basically max of payoff or 0. So you do not have any more option to exercise. So your continuation value is 0. And if you exercise, you get payoff, HST, right? So this is the value of the option at capital T. Suppose we know the value of the option at Tm plus 1. Then the value of the option at Tm minus 1 is nothing but maximum of payoff at Tm minus 1, or whether you continue or you exercise. The value of continuation is given, which is known as the continuation value, and it's denoted by Q in the slides here, is the conditional expectation of the value function at Tm given information at Tm minus 1. So that's what is given by equation 8. So in our regress later with neural network, we are precisely going to follow this formulation. What we try to do is we want to find a functional approximation to Vtm minus 1 such that the continuation value or the conditional expectation of VTM can be computed in exact form. So that is the approach that is followed, and this is what is typically known as the regress later approach, where you first approximate the value function V, and then you compute the conditional expectation of V in some closed form. The challenge typically lies with the approximation of V, and this is what we try to sort of nicely address with this neural network. So the algorithm which we call regress later with neural network starts like any other dynamic programming based Bermudian option pricing algorithm by generating sample paths, n copies of the sample path, starting from T0 until the maturity time T. Then you compute the value of the contingent claim at the maturity, which is straightforward, and the boundary condition. And then the following recursive strategy is followed. Let's assume that we know the value of the option for all the scenarios going from n is equal to 1 to capital N of the asset parts at Tm. So you know the option value for all the stock prices that are generated in your Monte Carlo sample at TM. And what we do next is that we find a functional approximation for this VTM. Right? So this is a straightforward supervised learning algorithm where you have STM, the input, and the output is VTM that you want to learn. And typically, the way it has been done is using linear regression, which is sort of nice, but it doesn't exactly fit VTM, or it doesn't guarantee an exact fit. However, a neural network, by the virtue of universal approximation theorem, sort of guarantees that it will be able to fit this function exactly, although there is no guarantee that you would be able to find the optimal parameters, but at least in theory, you should be able to fit this function precisely. So once you have this function G, the next step comes at computing the continuation value, which is the conditional expectation of V, which now, instead of computing the conditional expectation of V, we compute the conditional expectation of the approximated function. So this is more or less the algorithm. Now the challenge is, what should we use for approximating, or as an approximation architecture for G, and how do we compute this conditional expectation for G? Right. So we need to ensure, one, that G is flexible enough to approximate V to any arbitrary accuracy. And we should also ensure that the conditional expectation of G, once you have the functional form, should be known in closed form. So if these two criteria are satisfied, you can quite easily run this algorithm and obtain the option value at time t0 and also at any other simulated scenarios along the path. So like I said, the best choice, or the easiest choice for ensuring A is to use a neural network with a single hidden layer, because the universal approximation theorem guarantees, if you choose an appropriate activation function, that you can approximate V with arbitrary accuracy, for even with a single layer of neurons, single hidden layer of neurons. So we decide that we'll use a neural network with a single hidden layer. But our choice of the activation function is sort of gets restricted because of B. So we cannot use any activation function, because it could result in conditional expectation forms which are untractable or difficult to approximate. But what luckily turns out to be quite nice is that if we use ReLU activation function, one, we are able to obtain closed form conditional expectation. But the other more important thing is that we sort of show that you can hedge any contingent claim using a set of options. So that sort of comes as a byproduct, which is quite nice in my view. Right. So as discussed earlier, the choice of our approximation architecture at time TM is then a single-layered feed-forward network, where beta is the set of free parameters, which is the set of weights and biases that you need to fit. And the A1 and A2 are the affine functions that transform or project your input to a high dimensional space, and psi and phi are your activation function. So the particular choice of activation function is discussed in the next slide. Uh, uh, P is the number of neurons in your first layer, and the number of neurons in the second layer is by construction 1. So because you want your output to be in R, your option value resides in R. So that restricts the, what should be there in the final layer. So here D is the dimension of the underlying option. So if you have an option on 2 assets, then D is 2, and P is the choice that you have. So that is the number of neurons that you use in your neural network. P also would translate to something more financial, which I discuss in the coming slides. So the first hidden layer, we use ReLU activation function. ReLU is nothing but a max of the input or 0, right? And you can easily see that, you can see the connect with this ReLU activation function and payoff of, typical European option. And this is what also led us to sort of make a realization that, this is an approach of static hedging. The second activation function is basically a linear function. So you just output what you input, and that's quite straightforward. So what you need to do is, in order to determine these free parameters or the weights and biases, you want to minimize the least square error between V, the observation, and your the output that you obtain from your neural network. And this is done using stochastic gradient descent. Although in our case we use the variant, the popular variant, which is Adam, and sort of makes a lot of difference in arriving at the optimal values of theta. So the training set is the parts that you have generated for your samples, and that would constitute your training set. Now, the thing that I now move on to is the interpretation of this neural network, which I think is the more interesting part of the talk. So the output of the first hidden layer can be seen as, you have P options, basket option, with the weights for each of the option given by W, the matrix W1, and the strike for each of the option given by this bias B1. So O is a vector of option. Each individual option is given by OI, and that is nothing but a basket option, arithmetic basket option. The weights are Wij for the component X, and for the ith option, and the strike for the ith option is Bi1. Right, so you have P arithmetic options. Now, what is the quantity of these arithmetic option that you need to hold is what comes out from the second layer, which is basically the weights omega I for the ith option, right? So, and B2 then is the amount that you hold in your money market account. So the second hidden layer performs, sorry, the first hidden layer helps you determine the weight of your arithmetic basket option and the strike of your arithmetic option that you use to hedge this contingent claim at TM. And the second layer helps you determine the quantity of each of these options that you need to hold and the amount that you hold in the money market account. Now, by the universal approximator theorem, we know that G is going to replicate V with arbitrary accuracy. So if it replicates the option at Tm, at any time prior to Tm, between Tm and Tm minus 1, where Tm minus 1 is the next exercise opportunity, the option that you're trying to hedge, and this portfolio of basket of options would always perfectly replicate each other. This comes from the no arbitrage assumption. Sorry, and this is what is meant by the static hedge. So once we have determined G, which we now know is a set of basket options, we can compute the value of G at any time between Tm minus 1 and Tm, which is basically the value of European basket option. You know, if we know the expression for this basket option in closed form, it's quite nice. Otherwise, you can use some approximation theorem, right? For the specific case of GBM process, what we realized was if instead of using G on STM, we use G on log of asset price, the closed form solution for this weighted basket option is quite easily obtained. And you know, then for any contingent claim on a GBM process, you know, you have an architecture which can sort of handle any kind of option with any payoff without having to change anything in your pricing library. Right, so this G then constitutes your static hedge. Although I call it static hedge, it's semi-static hedge because you make an assumption of the model. So you, when you're calculating the conditional expectation of the payoff of G, you assume a model in which the process S evolves. And that's why it's technically a semi-static hedge. But if you know you ignore the model assumption, G is a set of while G is a neural network, it represents a set of options that are going to replicate your option that you are the contingent claim that you're trying to hedge or price. And it consists of short maturity options that mature at Tm. The payoff of these options are determined by the optimization of this neural network. And once you have these options, you can always compute the conditional expectation of G anytime prior to Tm. And this portfolio would also hedge your V or the contingent claim that you're trying to price at any time prior to Tm. Right. So here I just sort of intuitively explain, this universal static hedging property of this neural network, but the proof of convergence and therefore the claim that it's going to be a universal static hedge can be found in the preprint of the work that I did together with my PhD student Vikrant and Vikram. So one of the nice outcomes of this particular approach is that, there were questions in the previous presentation. How do you sort of be sure that your neural network has arrived at the optimal weights? Because quite unlike linear regression, where you know that you obtain the optimal weights, in this case, you're not guaranteed. There is no mechanism by which you are sure that you have obtained at the optimal solution. We can sort of get an idea how optimal the weights are by bounding our results with a lower bound price and an upper bound price. Lower bound price are typically quite straightforward to obtain. You obtain the policy, the early exercise policy through your backward iteration. And on a fresh set of parts, you follow this policy, you get the payoffs when you exercise these options following that policy, and you discount them accordingly. And because this policy is most likely suboptimal, you get a discounted expected value, which is a lower bound to the true price. So that's how you obtain the lower bound. The upper bound for the true price can be obtained using the duality-based approach. Now, the typical challenge with the duality-based approach is you need to construct a martingale process. And this construction, when you use a regress now scheme, requires sub-simulation. So for each simulated scenario, you need to again sub-simulate your paths until maturity, and then you obtain, a conditional expectation, which is then goes into construction of this martingale, which can be computationally quite intensive. There have been work around, how that the computational complexity can be brought down. But the nice thing about this regress later approach is that this martingale sort of comes absolutely at free cost, with no extra sub-simulations. So basically, the upper bound algorithm is obtained using this duality formulation, where you want to find the super martingale, which ensures that your the value that you have obtained in the right hand side is always greater than equal to the true option price, and the infimum of this would be the what we are trying to look at. Now, in order to construct the martingale, you need to compute. You need to minimize this equation in 12, and the key thing in there is to construct this MT, which is obtained, following this particular recursion. So you you go along a path, you look at the value of G at Ti plus 1, and you look at the corresponding value of Q at Ti for that same path, right? So this is what is obtained in 13. Now, by construction, conditional expectation of G is equal to Q. So M is going to be a martingale. You do not need any simulation or sub-simulation here. And that's therefore doesn't add any cost to your computation. And once you obtain M, you can obtain the upper bound using this particular expectation. This is something which is very nice, that you get both a lower bound and an upper bound, along with the static hedge for your for hedging your contingent claim, all out of this regress later with neural network. Now, a little bit more detail on the hyperparameters that we use. So we use Adam with the default parameters that are set. So initial learning rate is set to 10 raised to power minus 3. We use mini batch gradient descent algorithm. The batch size is chosen as 1/10 of the total training points, which are typically 50,000 training points. Something that I did not cover here, but you do not really need a very accurate discretization scheme to generate your training points, because you are fitting an exact function, and therefore the choice of measure for generating this scenario becomes redundant, and that's and the measure is taken care of when you compute the conditional expectation of this in closed form, and therefore you don't really need a sophisticated discretization scheme. But yeah, that's beside the point. Now, for training the neural network, you need as many neural network as are the monitoring dates or the early exercise dates. So for you have one for the terminal time and then one before that and so on. The most challenging part is to train your network for the terminal time because because of the kink in the function. But once you have trained that, this trained network or these network parameters can form as the initial guess for the network that you want to train at TM-1. So there is some transfer learning that happens, and it sort of makes the process much faster, right? So we, the reasoning is that VTM-1 is basically the diffusion of VTM. So you can start with the optimal weights for VTM as your initial guess for VTM-1, and then you are more or less sure that you are close to the optimal, and in few iterations you sort of obtain your optimal weights for TM-1 and so on. So we take the typical, precautions to avoid overfitting. So you divide training and validation set, and and you have these early stopping criterion, so you do not overfit your model. Also, what really helps is that you initialize the initial asset price to 1 and appropriately adjust your strike, and this helps to use the same set of weights for any initial state for which you want to price the option. For the examples that we have considered, we use 50,000 training points, and for this set of experiments, we only consider geometric Brownian motion. Right. So this is the results that we obtained for max option, which has typically been more difficult Bermudian option to price because of the non-linearity of the max payoff. And what we see is that we get pretty accurate results. Although when we move from 2 asset to 5 asset, the number of hidden units that we need to use in our neural network, or the interpretation of which is the number of options that you need to use for statically hedging your this max option. You need to increase those options, but you sort of obtain pretty accurate values. You see that you obtain a lower bound value and you also obtain an upper bound value. In the paper or preprint, you sort of get an interpretation of these lower bound, the financial interpretation of these lower bound and upper bound values. Very briefly, the lower bound values are more from the point of the person who is going to exercise the option. So, if you follow a suboptimal policy in your exercise, what's the loss that you're going to make? And the upper bound values are more for the hedger or the writer of the option. So if your hedge is not perfect, what is the loss that you make on your risk neutral price? So that gives you the upper bound. What we see is that the standard error of the upper bound values are order of magnitude lower than the standard errors of the lower bound values, which is sort of nice, especially if you are using this method for computing your sensitivities and so on. The bounds that we obtain are as good as any other in the literature. And you see that we did go to like Christoph to 100 asset option, but for 5 asset max option we do fairly well. This gives the convergence of the method with increasing number of neurons, which also sort of translates to the number of short maturity options that you hold in your static hedge. So if you increase the number of short maturity options in your static hedge, you replicate your contingent claim much better, and therefore you have lower upper bound and lower bound errors. While if you use fewer of those, you sort of have higher errors in your estimation. So there are also results for other options, multivariate options in with GBM process in our method in our paper, and we see similar results, and we are quite happy with the results, more or less. Right. So if you want to look at more details on some of the aspects of this work, as I said earlier, it's available in the preprint that's available at SSRN. So please feel free to look at the paper, and if you have any doubts, please reach out to me. I'll be very happy to respond. And these are some of the references.
All right. Thank you very much, Shashi. Again, an applause from my side for a very nice talk. And the chat is open for questions. A question from my side, Shashi, is it's very nice that you have this interpretation. Can you think of when I know you're also an expert in valuation adjustments and exposures. Can you see an application of your methodology in that context, in the context of valuation adjustments and exposure and hedging in that context?
Yeah. The key process here was at any time t, if we know the value function, you can replicate that value function with this neural network. So that comes just from the universal approximator theorem, and this particular choice of ReLU gives a financial interpretation. So whether it's exposure calculation or this contingent claim pricing, you first compute the exposure either by backward iteration, or you have another algorithm which gives you the exposure for different choices of the asset price at t. You fit this neural network, and this then results in finding the options that you need to hold to replicate this the exposure at this point time t. And once you know the set of options that replicates your exposure at time t, you sort of know its value because it's just European option, its value anytime prior to t, and you can apply this mechanism and this interpretation to whether you're doing a CVA calculation or whether it's pricing contingent claim.
Yes. So is it something like, what is the perfect netting? What is the perfect netting contracts that you need to hold with your counterparty? Is something like this?
So it's basically you have a payoff at a complicated payoff at capital T, and you want to find out, and there is no exercise between 0 and t. You want to find out the set of options that you need to hold right now, such that you would always replicate this exposure from this future payoff. So it's replacing your dynamic hedge with a set of options which will always. So it's basically an extension of the put call parity. And replacing one portfolio with another portfolio. The only good thing is that the other portfolio is much more tractable in terms of pricing or doing whatever with it.
Yes, I see 3 questions on the chat from Edouard. At t = 0, one finds the weights for the replicating portfolio. Is that it? How stable is this replicating portfolio over time, taking into account the Bermudan features? How often should one recalibrate, retrain, and how expensive is the calibration of the neural network for 5-dimensional versus finite differences?
Okay, so I'll address them one by one. Now, for path-dependent contingent claim, where you have early exercise opportunity, you wouldn't have a replicating portfolio directly from zero to your final expiry capital T, but you will have a replicating portfolio that would ensure that you replicate the payoffs until the first early exercise opportunity. At the first early exercise opportunity, this replicating portfolio would have, would give you sufficient return to set up a replicating portfolio that would hedge you from T1 to T2. The only thing is the weights of this replicating portfolio will not be the same as that at T1. So what you have to do is you set up a replicating portfolio at T0, which protects you till the first exercise date, that is T1. At T1, you unwind this replicating portfolio and you would set another portfolio which will protect you from T1 till T2 and so on. So the weights of these replicating portfolio at T1, T2 up till TM are sort of in our algorithm obtained in a dynamic programming way. So first you obtain the weights at TM and then you go back till you obtain the weights at T1. Now the thing is that if we assume, there is a model which the world, which generates these asset prices, then you don't typically need to recalibrate your this replicating portfolio. So once you set the replicating portfolio, you don't have to worry till T1. You just sit with that portfolio. It will always be hedging you against your claim that you are trying to hedge for. But the model parameters change, so the volatility that you had for your GBM process will change, and that's why you might have to adjust your replicating portfolio. But there's a more practical problem that that is there. At the training time, I sort of believe that talking about computational time for neural networks where you use stochastic gradient descent is sort of pointless, because if you start with the initial guess, which is far away from your optimal, it's going to take you a lot longer to reach to the optimal solution. Having said that, that your model parameters are not going to change quite quickly. So if I have calibrated my model today, the weights of my model are close to the optimal tomorrow, and that's why I can very quickly get the recalibration can happen retraining can happen quite quickly. So it's difficult to say the time it takes to sort of train the model, but it's quite quick. It's quick, but it's not as quick as a linear regression. So linear regression is fantastic when it comes to computational efficiency, and I think that was the reason why everyone was using linear regression. But now with the modern hardware, we can sort of live with stochastic gradient descent, and the method, you get results in less than a minute for 5 asset tasks.
Thank you. Carlos has a question. A similar question. Comparison of computational times between neural networks and, for example, binomial trees. And what when you have more than one neural network layer? So
like I covered part of the answer, but once you have trained your network, the neural network is much faster than binomial tree. Once your weights are already determined, training is a time thing which would cost you time, and it doesn't take too long. right? And to be honest, I'm pretty sure that there can be much that can be done in improving the efficiency, because you have a fixed architecture, so you can tweak your parameters to, it's not a very general model where you have different activation functions. You have made a concrete choice on the activation functions that you use. So, you can always tweak your method to make it much faster. But it's not too, it's less than a minute for the neural network, along with training. Now, for the second question, right? Like, what happens if you have more than one layer? The challenge that comes with more than one layer is this conditional expectation. With a single layer, this conditional expectation is basically the conditional expectation of a portfolio of basket option. But when you have two layers, you basically are talking about portfolio of option on option, right? So if you can compute that, it's this conditional expectation, it's quite nice. And this is something that we want to try in the future. So if you want to hedge your volatility risk, you would like to work with option on options, and this could be a nice thing where you have not just a single layer, but you have more than one layer.
I see a question from Balint. Balint also says, okay, you have your analytical expression for the shallow neural network. Do you see a way to generalize? You already mentioned the compound options. And are you aware of any smooth activation function with this method would allow for?
I'm pretty sure, that we could have an activation function, but the choice of them are quite large out there, for which you can compute the conditional expectation given your problem. But the nice thing about using ReLU here is that you have a very nice economic interpretation of your. So you are basically finding put call like parity. The choice of option payoffs that would replicate your value function, and that's why I worked with ReLU, and I like it because you have an economic interpretation. You can go and hedge your derivatives accordingly. But yeah, I'm pretty sure that there would be other activation functions where you can compute this conditional expectation either in closed form or use FFT or something like that.
All right. Maybe a final question from Edouard. How do you produce the data set for training?
In our case, we just did a Monte Carlo simulation for simulating the asset prices, and then the value function at the terminal time is known. Once you know the value function at terminal time, you are able to obtain the value functions at Tm-1. So you again have this supervised learning setting, and then you can go back iteratively. So that was the dynamic programming thing.
All right. So thank you very much for your answer, Shashi. And with this, we come to the end of the first part of our workshop.